So welcome everyone to today's GDS tutorial. Before I turn it over to the speaker, I have just a few announcements. If you or someone you know would be interested in doing one of these tutorials, please email me at the email address at the top of the slide here. Or if you have a topic that you would like to see in one of these tutorials, please send that as well and we can find a speaker for that topic. If you have any feedback for us, something we did good that you think we should continue, something you think we should change to improve everyone's experience at these tutorials, please use the QR code on the left side of the screen to leave us some anonymous feedback, and I will be posting the links into the chat after I'm done here. The materials that we will be using today can be accessed through this middle QR code and bit.ly address. It will take you to a GitHub repo. And the materials for today are under the folder that starts with today's date. And then if you're not already a member of GDS, the APS's topical group on data science, I would encourage you to join using the QR code on the right of the screen. Being a member of GDS means that you'll get announcements to the tutorial series along with many other programs we run. And if you already have an APS membership, then adding GDS as a topical group is only an extra $10 every time you renew your membership. The next tutorial will be in about a month, on the 22nd at 1 p.m. Eastern. The topic and author are still to be determined, but as soon as that has been settled, I will send out an email to all GDS membership alerting them to the new topic. If you have an interest in viewing any of the past recordings on like unsupervised machine learning and physics-informed neural networks, amongst other topics, you can scan this QR code here, which will take you to the playlist on YouTube from the American Physical Society with recordings of all of the past tutorials. There is a link in each of the descriptions to the materials being used by the speakers if you would like to follow along with them. And all of the materials are also on the same GitHub repo that we'll be using today. And then finally, GDS has a new feature, especially if you are a student, a postdoc, or an early career member, and you have recently published a paper in a peer-reviewed journal that you think would benefit the GDS membership at large. Please scan this QR code and fill out the form, and we will be happy to highlight your work on our website and also on our social media. And so with that, I will stop sharing and turn it over to our speaker.
Fantastic. Thank you very much for the introduction, and let me share the screen. Here we go. So generally, what we are going to talk about today is the principles of the decision making. So I will illustrate some simple approaches like bandits and Bayesian optimization, and briefly illustrate how this can be extended to the reinforcement learning and stochastic optimization. So just as the quick introduction and setting the problem, so I worked for almost 20 years in Oak Ridge, then I spent a year in industry in Amazon Moonshot Factory division. After that, I joined the University of Tennessee. And when I joined UT, some of my colleagues have been working on the combinatorial material synthesis for more than 15 years and combinatorial processing using the in situ laser beams. Some of my other colleagues started to work on the high throughput synthesis and the robotic film deposition starting from 2019. So when I joined the UT, my program became the use of the automated scanning probe microscopy. So we have the SPM that can send the data to the supercomputer or other cloud resource. The data can be analyzed and the control commands can be brought back to the instrument. So working with my colleagues in electron microscopy field, we build the same type of automation for the electron microscopy. We build the same type of automation for the non-indentation. And now we are working on the implementing the automated X-ray measurements primarily for the complex microstructures and the combinatorial libraries. And with working on all these problems, the first question that comes to mind is how are we going to make all these tools work? And secondly, how are we going to make all these tools work together? So the obvious and, as you can imagine, very partial answer is that we are going to use machine learning. But machine learning is a very dangerous field now. So it's a field that has a ratio of hype to solid outcomes, which is about 100 to 1. So the question becomes, if you're an experimentalist, if you do things practically either with experimental or theory workflows, how to cut through this hype and basically come to the solid of understanding of how and when to use the machine learning. And my general advice would be try to divide the problem into two parts. The first part is how to make the decisions. And obviously decisions can be made by human or decision can be made by AI or some combination thereof. And the second part is how the decisions can be executed. So some of decisions can be executed by human, some of the decisions can be executed by instruments, some of the instruments can be automated. So if you start thinking about building the autonomous tools, the autonomous labs, you can ask the questions of how fast can decisions be made? How fast can they be executed? What decisions can be executed? How are they improved? So this will give you a framework that allows to map real-world problem on some combination of machine learning and human decision-making and execution. If you come more from the machine learning part, the things that are worth thinking about is how to make machine learning real. So for example, a lot of people talk now about using the ML and reasoning systems for the hypothesis generation. But if you stay purely on the computer science side of things, everything is limited by how much data you have and how much compute do you have. If you are living in the real world, each hypothesis requires an experimental footprint. So if you want to find something within a single sample, you just need a tool. If you need to combine synthesis and characterization, you need a combination of synthesis labs and characterization, then everything becomes much more slow. Another big difference between the pure ML world and the experimental world is that we know that in computer sciences, the more data, the better. So the success of large language models and similar technologies is predicated on the availability of essentially a full corpus of the human text data. In experiment, the principles are very, very different. So for example, if we run experiment, we of course want to collect as much data as possible. But if we plan the experiment, we want to be able to get the answer with as little data as possible. So the typical experimentum crucis that if you have a hypothesis, you want with the binary outcomes, true or false, like finding the Higgs boson or whatever, you want to plan an experiment in such a way that you can get the answer with only one experiment. So the question becomes, how can you learn to do this type of things? And how can you bring machine learning to the experimental world? So in my observations over many, many years working in the user facility and then teaching ML, there are 4 levels. We can separate 4 levels of the machine learning application. So the first one is using ML to solve the established problems. So traditionally, you would need to learn Python for that. Now, with the coding assistance, the activation barrier is very, very low. So if you know what you want to do, the ChatGPT or similar coding systems can help you to do that. This, of course, doesn't solve the problem in full because you are effectively kicking the proverbial can down the road. You will still have to learn how to program, but you can do it considerably later. The next big step is being able to use ML, use the new concept that ML offers. For example, if you work with the variational autoencoders or decision making, it gives you the access to the new level of abstractions and way of thinking about the world. And very often that opens the pathway for new research. So for example, my work for about 3 years was focused on using the new science enabled by the latent representations of variational autoencoders for physical problems. And today's tutorial would be pretty much about what is the decision theory and how we can use it for experiment. More complex step is the representation of the real world in ML abstraction. So we all know that science becomes real if it becomes mathematized, sort of going back to Lord Kelvin in 19th century. But practically, there are objects that are relatively easy to represent as machine learning abstractions. For example, chemical formulas and molecular biology. But for materials, many physical concepts and so on, representation is a problem, and it's not explored even in machine learning community. And most importantly, if you want to make machine learning a part of your research or business workflows, that's complicated. You really need to think not in terms of tasks, but processes. You need to define the reward functions while you're doing things, heuristics, how to predict the decisions, if you will, or ascertain whether they are likely to be good or bad, and so on. So practically today, we are going to talk on how to use ML for decision, but keep in mind these steps as well. So what do we have now? So currently there are two primary paradigms for ML. One is the theory-based workflows that people have been working actively starting from Gersider's paper about 20 years ago. Another is the experimental workflows that have been around and growing exponentially for the last 5 years, which are primarily based on the Bayesian optimization. So I'll illustrate the Bayesian optimization down the line, but let me just point that real world is very different from theory-based prediction or Bayesian optimization. So in the real world, we always have to deal with the multiple decision-making steps. For example, if I illustrate the workflows in a lab for making hybrid perovskites, sometimes we need to use the data from the microcrystal library to choose what thin films to fabricate. This is something that can be done using multi-objective and multi-fidelity Bayesian optimization. Sometimes we use the data from cathodoluminescent experiment in order to understand the physical mechanisms, and based on this understanding, propose a different manufacturing pathway or choose different end members for the chemical space. Machine learning cannot do it, at least not for the time being. This is a very, very complex decision. And even if you run a single tool, the decision-making process is actually not trivial, because imagine that you are sitting in front of the electron microscope, you can zoom in, zoom out, you can take spectra. The number of operations that you can perform on the instrument is actually very, very small. But the number of operations in terms of how many of them you perform during the day is very large. And even the same person, even if you have the same sample and the same microscope, but the person who sits in front of the microscope have different goal, will structure the experiment differently. So this is a linear workflow, but it's a linear workflow that's informed by prior knowledge, and it's the workflow that is aimed to lead you to the certain outcome. So in microscopy, we can represent the operation of the instrument as the set of operations, and essentially the role of the decision making becomes to choose what next operation to take. And two words that I would like you to remember is the word policy and the word reward. So policy is essentially a lookup table. This is what I see on the screen. This is what I'm going to do if I see this. It's essentially can be a rule table. Reward is what I want to accomplish. So if we want to get a reward, we actually need to learn the policy. The policy and rewards can be defined on a single step, or the reward can be defined in the end of the experiment, and then you need to go through the experiment multiple times in order to figure out how to accomplish this reward. However, we cannot, if we don't have policies or rewards, if we only have an objective, then machine learning does not apply. So if we say that I want to discover a better material for a battery, and I want to somehow use this consideration to drive the experiment, I cannot do that. It's impossible. It's like having mathematical equation when you have expression on the left, equality sign, and then you have nothing on the right. It's an incomplete problem. So
There's a question in the chat real quick. Do you want me to read it to you?
Let me see if I can open the chat. Absolutely. Okay, so this is a very good question. So no code is a convenient force acceleration. Generally, I would argue that this is impossible because coding primarily teaches you how to structure your thought process, and how you implement it depends on what the tools are out there. So 50 years ago, people used the binary code. 40 years ago, it was assembly. Then we had the high-level languages like basics, whatever. Then it became C. Now we use Python. With LLMs, we can use the coding enabled by the coding assistant. But it works for only specific tasks. And if you want to build the whole workflow, things start to fall apart very, very rapidly. So you are not going to be able to build a workable system with the vibe coding. And another thing is that this type of no-code approaches work if you already understand what you want to do. And for that, you simply need to have a hands-on experience in order to develop the intuition that allows it to do that. So in my experience, for people like me who are casual programmers, no coding or code assistants are great force multipliers. So my work as the programmer is really going to the level of time 10 with these tools. But for the professional coder who works on a very high level, they are much less useful. So anyway, these are the definitions that are really worth knowing. So there is something that we want to achieve in the long term. A reward is the measure of success that we have available at the end of the experiment. It's very important to have what is called value or expected reward. And in fact, many of the active learning methods like reinforcement learning use the difference between reward and value as the feedback signal. And then, of course, as I mentioned, there is no computation without representation. So we need to define what is that we can do. So this is called action. Practically for automated tools, this is the code that can be executed on the instrument. It can be something else. It can be operations you can do in the lab. And state is basically what the machine learning agent knows about the system. So policy is a rule book that defines actions given the state. So notice that all these words, they have meaning only when they combine to each other. And it actually takes quite a while to get intuitive understanding of their meaning, and especially figure out how to make them work for the real world problems. So let me illustrate some of the examples. So imagine that you run the experiment like this. When you have some material surface, you can take measurements in the individual locations. You want to run the experiment when you want to understand structure-property relationships. So what would be the reward in this experiment? So it turns out that if I start to work on the instrument, first I will try to make my instrument optimized. So I want to improve resolution or some form of other instrument baseline. Then I want to study the regions that are most present. So for example, this type of patterns. But if I have the same behavior here, here, and here, there is no need for me to study this one and this one. Then I can say, look, this looks very unusual. So how about I see what happens in those locations? But some of my colleagues can tell me that, look, the reason why you want to study this type of objects is because you expect to have some unusual physics here. And by the way, you also have to study these objects because here you have, let's say, flex electric coupling between the strain and, let's say, conductivity. So notice that the operations that you will perform are almost the same. It's essentially point and click. But the reward function changes throughout the experiment. We start with the microscope operation, then we explore statistically significant regions, then we are driven by the curiosity, and then we are driven by the falsification of the physical theory. So the point that I want to make is that unless you explicitly formulate your reward function, and you don't and unless you cannot express it in the form of the code, you will not be able to run the automated experiment. However, once you can do that, then automated experiment becomes purely engineering problem. So you need to have an API and you need to be able to code. So the caveat is that decision making by humans, so how do you pick the next location or next experiment in the lab, can be very, very complicated. And the second thing is that when we talk about decisions, you can always think about the branching tree of the opportunities. So one decision unlocks two more decisions, next decision unlocks more decisions. So basically, if you try to collect the data, then your space of opportunities expands exponentially. It's impossible. However, if you make right decisions, then it is only linear. So there is a very good reason why good decisions are much better than the big data. It's much more consistent in terms of the experiment. The problem is that our decisions are usually much more complex than just something straightforward. For example, imagine that you test a battery. There are multiple parameters that you want to optimize jointly. So this becomes a multi-objective decision making. Same thing applies for anything else. So if you run the experiment on the robot, or if you run the instrument, you want to get a better data, you want to spend less time obtaining it, you want to not blow up the instrument, and so on and so forth. When you make decision, we also combine multiple sources of information. So for example, if I choose what next material to synthesize on the robot, I usually base my decision based on the simple theory, right? We all know Arrhenius law, what's not. We usually use the data coming from different experiments. Sometimes we are informed by the results from the DFT or something like this, even though we don't expect the DFT modeling to correspond to experimental reality one-to-one, it still kind of suggests some form of generalities. So human decision-making is super complicated, and at least at this point, machine learning doesn't come even close to being able to adopt the level of human decision-making. So what we can do with machine learning is do things faster or with the bigger data volumes, but that's usually a combination of the two. And third thing that is super important is for automated experiments, is to translate your long-term objectives into the rewards that can be a part of your automated workflows. For example, if you want to reduce global warming 30 years from now, we need to make cheap materials for energy storage. Let's say 20 years from now, 10 years from now, we need to understand mechanism for the cathode degradation. That's what we want to do in 2 years to build a battery. And only, and based on this, we speculate that today, when I'm running the instrument, what I want to do is to run electrochemistry in situ on STEM and observe how the cracks develop. So this is the reward that can be realized today. Everything else is probabilistic and in the future. And if we want to plan the automated experiment, we need to have a measure of success that we learn during the experiment. If we don't have that, forget about automated experimentation. Let me show you a few examples how it works. So a simplest example of the automated experiment is what is called the fixed policy experiment. So in this case, you already have the reward and you plan the policy before the experiment and you don't change it. So this is a very simple example of the experiment when we look at the nanoparticles in the electron microscope. We segment them using the machine learning model, and then we basically tell our microscope to enumerate this particle and take the yields, EDX, and diffraction data one particle at a time. So you see this is the particle we study. We take chemical composition, diffraction, and vibrational spectra. Then we choose this particle and we do the same thing. So the benefit of this approach is very clear, because imagine doing it point and click manually for several thousand particles. And of course, if we run the grid measurements, most of the measurements are useless. So in this case, we can clearly quantify what is the advantage of the fixed policy experiment compared to human. This is another example of the similar experiment. So in this case, we also go through some complex microstructure, and then our microscope takes measurements on randomly chosen locations on the step edge, on the domain walls. So we can run, of course, more complex experiments. So this is one of the first examples of the automated experiment we were able to realize in about 2020. So the electron microscope takes the data, and then it converts the data in real time into the atomic positions. This actually ended up being fairly complicated because the neural networks have what is called out of distribution drift. And it's very difficult to build a network that can be robust if we change the resolution or imaging parameters. But if you do that, then we can do some interesting fixed point experiments like atomic manipulation. So if I look at the molybdenum S2, I can tell my electron beam to follow the straight line. And the electron beam will kick out the sulfur atom. So we wrote the letter R based out of the defects in the molybdenum sulfide. So this is
There's
an example.
another question in the chat if you have a second.
Let me see if I can get it.
I can also read it if you like.
1 second, I should be able to get. Okay, so regarding objective 3, most AI cannot reason. Secondary effect is out of scope for ML algorithm. How does error p-value benefit to your work? I mean, this is a very, very complex question because it spans many different things. So practically, my general principle is that if we can use physics, we should always use physics. So we use machine learning for rapid decision making, or when the physics is not available or known only partially. So the reasoning systems help us make guesses, but of course it's, at least for now, is suicidal to let them control the instruments or do science for you. But as an assistance, they are fantastic. So for things like p-values, I mean, p-values make sense only in the context of the frequency-based statistics. Practically, I firmly stand in the Bayesian kind of camp for this type of stuff. We always interpret the data in the context of the prior results. So frequency-based approaches work when you have a lot of data and you somehow manage to isolate your model system from the outside world. So most of the world is not like that. Okay, so anyway, going back to the rewards. So another interesting example of reward is the physics discovery. So how would it work? So intuitively, we understand that the correct theory or correct model will describe experimental data better than the incorrect one. So it turns out that we can actually run the experiment when we have several different models that compete with each other for the time on the instrument. I will illustrate actually this approach when I talk about bandits, but for the time being, I want to illustrate how this approach works. So here you see how the machine learning agent that sits on this laptop talks to the scanning probe microscope, and the scanning probe microscope runs the experiment when it tries to switch the ferroelectric domain inside the material. So machine learning agent analyzes the experimental results in real time and tries to choose what theory gives better prediction, and then it allows this better theory to run the experiment with a higher probability next time. And this is how it looks on the back end when you see how our machine learning agent explores the parameter space of the theory. And here you can see that depending on the model prediction, we give the reward to the model 3 more often. And it turns out that for this particular material, model 3 is actually the right mechanism for the domain growth. So this is another example. So the typical problem in microscopy is the image optimization. Interestingly, if you have the atomically resolved image, imaging optimization is a relatively easy problem because we can always see how sharp is atomically resolved image because we know how the ideal image looks like. If you want to optimize the microscope with the mesoscale imaging, that's very complicated because we don't have an ambiguous measure of how good is the image. So what you need to do is you need to formulate the reward function. It's actually not trivial. You need to combine the human heuristic, so how human identifies the image as good or bad, and the knowledge of physics. But if you manage to do that, it almost becomes like a Coca-Cola recipe. If you have this definition, then you can use the simple optimization methods like Bayesian optimization, in order to optimize the microscope. Another type of reward is structure property relationships. So we generally talk about structure property relationships as basically a correlative relationship between structure and properties. And it turns out that if we define the predictive power of this model as the reward, then we can explore material microstructures, and we can even discover the behaviors that we're interested in. This is so-called deep kernel learning. I will illustrate you quickly how it can be done. And most interesting rewards are materials optimization. So as I mentioned, for each hypothesis, we always have a hypothesis footprint. So the minimum amount of equipment, we need to realize it. And for each type of experimental footprint, we will have a latency. So if you run synthesis in the PLD chamber and characterization in the squid, then your feedback time is about a day, right? You need to grow a sample, make a squid sample. So feedback is actually very, very slow. Machine learning is not terribly useful for this type of stuff. But if you somehow come up with a way to create multiple samples inside one sample, then the feedback can be very rapidly. You just go from the different sample sizes. And this is something that can be done by combinatorial library. So here you see how it works in the real time. And this is how it looks at the back end. So you basically have this is the representation of your 4-inch wafer. The red points that appear are the locations where the microscope takes the measurement. Come on. And what it constructs as the result is the Pareto front between the different characteristics of the film. So in this case, we explore roughness and the grain size. So in this case, the feedback is very rapid because we have the same microscope exploring the combinatorial space. So with these demonstrations, I've shown you only the examples of the active decision-making on the instruments. So obviously, many of my colleagues work on the similar problems on the lab robotics, in situ characterization of the film growth by PLD, and so on and so forth. So the question is, how can we solve these problems? Now, there is no way in the world I can explain the basic principles of the decision making. So it would be even the introduction would be a full semester course. But what I can do and what I will do is the illustration of the basic classes of this problem, so you know where to look. So for example, when I started to work in this field actively during the COVID time, I essentially lost a year because I decided that the right way to go is the reinforcement learning. Reinforcement learning is a very popular method. So if you talk to your colleagues in the ECS type of departments, they will tell you how great it is. Guess what? For the vast majority of the problems we encounter as experimentalists, reinforcement learning is pretty much the worst method out there, simply because the basic methods are purely data-driven and unphysical, and also requires a very specific setup in terms of states and rewards. So the idea of this tutorial is to give you some idea about what the methods are out there and where to start. Remember that we are experimentalists. We want to solve the problem by the easiest method possible, rather than go for the most complex way or most expensive way to measure the Planck's constant. And the easiest decision-making problems are so-called bandit problems. So this name, as you can imagine, comes from the Las Vegas and from the slot machines. And generally, these bandit problems apply for, obviously, being in Vegas, or figuring out how to place ads on the websites, or choose the groups of patients for specific medical protocols, or even the planning of the work inside the lab. So how do you do that? So first of all, whenever we talk about the decision-making problems, always go through objective, reward, value, action, state, and policy. If you cast your problem in terms of these components, then it would almost immediately be obvious what type of algorithm you can use. So for bandits, objective is get rich, right? So the reward is a payoff. So for example, what is the click rate of specific ad or payoff from specific slot machine? The value is expected reward. So notice the difference between reward and value seems to be quaint, but practically it's the difference between the outcome and your expectation. And the difference between the outcome and expectation is the feedback signal that helps you correct behavior. So action is straightforward. The great thing about bandits is that they have no state. So there is no information about the system. We just have actions. Policy is our game plan. So how can we solve these problems? So the most popular way of doing it is A/B testing. And A/B testing is so simple that it's kind of almost misleadingly simple. So you take our users, split into groups, and try two different strategies to see which one works better. In fact, as many of you probably realize, whenever we use Amazon website or any other type of customer portal, we are always A/B tested based on which ads work better, what products get solved faster, and so on and so forth. So that's why we always see slightly different versions of the website, and the companies try to figure out how do they work. That's also the reason why these commercial websites are so easy to use and intuitively clear, is because they have been optimized over tens of thousands of interactions. So in this case, the values are very straightforward, right? So the value of the next step is basically value of the previous step plus 1 over n of the reward minus the value. So that's a very easy way to calculate the value. Interestingly, in the ML community, initial value tends to be 0. In the real world, you probably will take it from some form of the human heuristic, because this will determine how fast your algorithm will converge. So we can generalize it. So rather than take into account all prior measurements, we can take into account some sliding horizon. So that makes it considerably easier. So what's the problem? A/B testing is super simple, but it's very inefficient, because basically if we spend a lot of time on the A/B testing, we don't generate much value. So we spend a valuable time for doing it. But at the same time, if we don't spend enough time for A/B testing, we can get a wrong answer. Secondly, A/B testing doesn't adapt to the dynamic environment. So if things change, we already have our protocol. We are not going to test it. And surprisingly, testing, A/B testing, comes with a certain number of hyperparameters, and tuning them is not simple. So remember that the big difference between the simulations and experiments is that simulation, you can do things many, many times, and you can tune things. When you do experimental time is priceless. We rarely have an option of doing things several times. And as the result, we need to be very, very cognizant of the experimental budgets. Otherwise, we simply run out of time. So other ways to do things better. So the most famous beyond A/B testing approach is called the epsilon greedy. So epsilon greedy is very simple. It basically means that we have the value of the steps. So based on our prior experience, we ascribe some value. It is our belief in reward. It's not true reward. It's our belief in the reward. And then epsilon greedy policy means that we most of the time take the action that we believe to be best, but with the probability 1 minus epsilon, we take a random action. So that allows us to explore, because sometimes we can get locked into the wrong action. And if we keep following it, we are not going to be effective. So epsilon greedy policy does, it divides our decisions between what we believe to be the best decisions and random decisions that allow us to explore things. So think about it this way. Imagine that you leave your lab and you want to go to the restaurant or to the beer place. So you have your favorite beer place, but you kind of know that there may be better places out there. So with the probability 1 and the epsilon, you randomly choose the unknown beer place because you think that it may be better. So I provided a notebook on the GitHub that allows you to compare A/B testing and different greedy policies. Notice a very important thing, that depending on how you choose your parameters, that affects your long-term benefit. So for example, in the beginning, you can learn faster with the less greedy policy, but your long-term returns would be maximized with the more greedy policy. So in the beginning, you want to be here or here, but long-term, you really want to be here. So that's kind of very important balance between exploration and exploitation. So what else is there? So, I mean, A/B testing versus greedy compare is relatively straightforward. So I provided some points on the slide, but it turns out that there are other ways of structure your exploration policy. And this is here, the most famous one is so-called upper confidence bound. So this is super important because we use upper confidence bound for bandits. We use it for Bayesian optimization. We also use it for things like the Monte Carlo decision trees, like people used in the AlphaFold. So here, what the decision-making principle is that we make a decision based on argmax, so the maximum over possible actions, of the sum of two components. This is our value. So this is our belief in how useful the action is. And this is the term, so this is a square root of logarithm of time divided by the number of time we try this action. So basically what this does is that if we did not try the action many times, then this term would be large, which means that it will allow us to explore the less explored actions. At the same time, if we have done something many times and we know that the reward is not particularly high, we are not going to do that. So this is a way to balance exploration and exploitation dynamically. And again, we can dig deeper into what it means and how it works. But basically, if it is your first year using decision making, probably upper confidence bound is your technique of choice. Further than that, you can find other methods of doing it. So again, I illustrated as a note some of the points about why the upper confidence bound policies is great. And with that, let's see what else can be done with the bandits. So a very important extension of the bandits is so-called contextual bandits. So the normal bandit builds the relationship between action and reward, and the contextual basis also takes into account a state. So what action give you better reward depending on the state. So there is a whole collection of books and blog posts about it. So my favorite one is this HackerNoon post that talks in detail about contextual multi-arm bandits. But basically, again, remember one thing, that algorithms for the bandits are available out there. If you want to realize linear or neural network or decision tree, that's actually pretty straightforward. If you want to use this type of approaches, you need to enumerate your actions, your context, your reward functions. If those are not available, you simply cannot use that. So these methods don't apply. Once you have them, then you can either do it by yourself or you can find someone who can help you do that. Now, let's talk about slightly different problems, which is the Bayesian optimization. So the bandit problem was the problem of the discrete choices. I can take this action or this action. I know that there is some ground truth about how useful these actions are. I don't know this ground truth, but I want to dynamically learn the right answer while maximizing my return. So this is what the bandit problems are. The Bayesian optimization problems can be generally formulated like this. So imagine that you have some parameter space. It can be phase diagram. It can be the control knobs on your microscope panel that allow you to tune the microscope. It can be processing space. It can be anything. So the first step, of course, is to define the dimensionality of your parameter space. Then you take a measurement in this space. So you take a measurement. It can be an image. It can be a spectrum. It can be mechanical property measurements. So then based on these measurements, you create a what is called surrogate model. So surrogate model is basically the scientific name for taking your a measurement and finding a way to interpolate it over the whole parameter space. So there are two caveats here. Caveat number one, very often our measurement gives us spectrum or image or something like this. In this case, when we build a surrogate model, we need to find a way to transform this high-dimensional data set into one of few scalarizers. Scalarizer is another word for the reward function. Why does it matter? It matters because if I explore the combinatorial phase diagram based on spectroscopy, sometimes I'm interested in the position of the peak, sometimes I'm interested in the width of the peak, sometimes I'm interested in the presence of some minority phase that I can see as a small peak in a different place. My exploration trajectory would be very different depending on how I choose the scalarizer. And if you work with your colleagues in the machine learning community, they will not be able to do it for you. They will be able to solve the optimization problem, but not define the scalarizer. And this is by now 90% of the work. So the second thing, which is very important, is that for Bayesian optimization, surrogate model have to give two things. One is the prediction, and another is uncertainty. So, and then if you have a prediction and uncertainty, you can combine them into the acquisition function. And acquisition function is basically a policy. So the typical acquisition function would be upper confidence bound, which is exactly the same upper confidence bound as we talked about in the bandits. So acquisition function tries to do is it tries to combine the uncertainty and prediction in such a way that the maximum of acquisition function is your next measurement point. So again, it is a subtle thing and requires a little bit of time to experiment with that, but it makes automated experiment possible. So now we are going a little bit in the boonies, and we are going to go through very quickly just to illustrate the basic concepts, which is how do you build this type of surrogate models. So here we have some interesting things, like imagine that you have 2 points. So you've done measurements in the one-dimensional space. This is your measurement number 1, this is your measurement number 2. So if you are a physicist or you think like a physicist and I ask you to find the surrogate model, you will draw a straight line, right? Makes perfect sense. So if you are a data scientist, you will also draw a straight line. Now imagine that I made a third measurement and the point is here. So what should I do? So option number 1, I can draw a parabola. Option number 2, I can draw a straight line, but in this case, the points are not on this line. So I have a measurement and there is a noise. I believe there is a noise in the measurement. So should I choose the parabola or should I choose the line? The answer depends on your beliefs. If we have reasons to believe that our measurement process is perfect, but we don't know much about theory, parabola is the right answer. If we have reasons to believe that this relationship should be linear, but our measurement system isn't perfect, we will choose the straight line. So practically, how you fit even 3 points depends on your prior beliefs. Why does it matter? It matters because beliefs is how we build the models. So the Gaussian processes, which is a very popular topic in the decision making now, is a very interesting mathematical object that starts with the belief that the measurement can be anything, but there is a correlation from one point to another point in the parameter space. So we don't have the structure, so it's not straight line or parabola or anything. We just know that the points that are close to each other, in the parameter space, have the somewhat similar behaviors. So I provided the 2 notebooks that introduce these comments, and they come with the extensive markdown fields, so you can play with them and kind of go through the code and the explanation. But this is roughly how it would look like. So for example, the correlations can be defined by what is called the kernel. So one of the typical kernels is the RBF, or the Gaussian kernel. So in this case, it's just the functional form. So if the kernel length is small, this is how your functions look like. If your kernel length is larger, this would be like this. If it is even larger, then the correlations are stronger, so the functions change smoother. So you see, the Gaussian process is almost like a Cheshire cat from the Alice in Wonderland. You basically take a physical object, a function, and take away all the attributes, instead the correlations. So as a physicist, we think very differently. We think in terms of structure: line, parabola, sine, cosine, whatever. And then we add errors. The Gaussian process basically takes correlations and removes everything else. And then now you can ask, so if we have this type of weird object, why is it useful for building the surrogate functions and the uncertainties? This is how it works. So imagine that we have not made an experiment. Our functions can be everything. Now we have run the experiment. So in the points when we have the experiments, we know what functions remain. And in all the other points, we can average them, and that gives us mean function and uncertainty. It's basically a trick, but this is an amazing trick, and it works. So how would we use the Gaussian processes for automated experiment? And first of all, again, there is a certain set of words you need to know, like Gaussian processes, kernels, priors, noise priors, posteriors, and so on. So to answer again the question about the vibe coding, imagine that you have to vibe code the automated experiment, but you don't know these words. Obviously, in this case, you will not be able to explain what is that you need. You might be able to go forward and backward with ChatGPT to learn, but that's already you learning, not their system. So how would we use this predictions and uncertainties to structure our experiment? Very simple. So imagine that this is our measurement, this is our mean function, this is our uncertainty. How do we choose, how do we make a decision where to take the next measurement? Very simple. We either will choose the location where we expect function to be high, or we will choose the location when the uncertainty is high, and therefore the function can be high. So it's a balance of exploration and exploitation, same way as with bandits. The way we do it is through the acquisition function. So as I mentioned, the most popular one is upper confidence bound, but there are many others like probability of improvement, expected improvement, and so on. And the way that the Bayesian optimization works is like this. You take the measurement, you calculate the surrogate model and uncertainty, you calculate the acquisition function, you take the next measurement where there is a maximum of the mean function, and then you repeat the experiment. That's all there is to that. The good thing is that this is a data-centric approach, and it tends to be very effective. The bad thing is that it is a data-centric approach. So very often we need quite significant amount of data to do this type of things, and it's limited to relatively low dimensional spaces. So this is kind of an example of the Bayesian optimization that tries to learn the phase diagram of the Ising model. This is the grid-based calculation, so ground truth. You can see how the very greedy algorithm explores the parameter space, so it finds only these locations. The caveat, of course, that if something was here, it will never find it because it's, again, very greedy. And if we make it less greedy, then we will spend a lot of time exploring less interesting objects. So there are a lot of ways how the Gaussian process can be expanded. So for example, there is a thing called what if the noise level is not constant? So there is a way to do it. It's called stochastic Gaussian process. It works. Caveat is very data hungry. If the noise can be measured, for example, we can measure not only the function but also the noise, then we basically use two Gaussian processes, one to predict noise, another to predict the function. So this is called measured noise Gaussian process. We can do other things. So for example, you can say that what will happen if our position is not precisely known. So we have uncertainty in the measurement location. So we can do that as well. So basically using the Taylor expansion of the function with respect to position. So there is an uncertain position Gaussian process. Caveat is that everything beyond simple Gaussian process takes a lot of data to converge. So what else can we do? So the biggest limitation of the classical Gaussian processes is that the mean function is assumed to be 0. So if you take the books on the Gaussian process, they will basically tell you that, look, we take the mean function as 0 because it's domain specific, and let's focus on building the kernels. So obviously RBF is the simplest kernel, but there are many more interesting ones. For us as a physicist, it's far more important to control the mean function than the kernel. So this can be done. So basically what it means is that instead of the mean function of the prior functions being anything only defined down to correlation, the prior function can be chosen from some physical model. So this is called structured Gaussian processes. There are several ways how this can be combined. So either through the defined function or through the probabilistic function, but they really work very well. So this is the example of the structured Gaussian process that tries to find this type of function. So the classical Gaussian process will never work in this type of scenario because it will never be able to find a rapid jump. It will only work by minimizing the kernel lengths, and that means a lot of measurements. So another interesting thing about the Gaussian processes is that they typically work very well only in the low dimensional spaces. So in the high dimensional spaces, the Gaussian process would be more efficient than the grid search, but it still will require a very large number of points. So it's like factor of 3 more effective, but not factor of 100. At the same time, if we have physical model like linear model or some parabolic model, what's not, it would be much more effective than the grid search because in this case, we just need to have a measurement for dimensionality. So the question becomes, are there techniques that allow us to use the Gaussian processes in the complex problems? And the important thing here is that we almost never have the problems of the exploration of the high dimensional spaces without prior information. For example, if we want to learn structure property relationships, it's not a black box problem. It's a problem where we have structures and we want to dynamically learn properties in the most effective manner. So a typical example, imagine that you run STM measurement and you have an STM image that's some form of atomic reconstructions, exacerbates, whatever. Question is, how are we going to run automated experiment? Option number 1, we choose interesting objects and measure them one by one. Option number 2, we try to build an algorithm that allows us to discover the objects that have interesting functionalities. And it turns out that this is also a Bayesian optimization problem. So I showed you STM example, can be the same type of thing with the electron microscopy when we have ill spectrum, we have the bulk plasmon and the edge plasmon. We want to discover the locations which maximize the edge plasmon. So how would we do that? In this case, we will learn a version of the surrogate model, which is called deep kernel learning. So deep kernel learning starts with the structural object, like the image patch, and it will try to predict the scalarizer, which is an area on the peak. And then once we have it, we basically take the spectra at several locations, we measure the properties, we train the model. So the deep kernel learning is essentially a hybrid of the deep convolutional network with the Gaussian process. And we will be able to predict the properties everywhere. So for measured objects and for unmeasured objects. And then, of course, if we can predict the properties and the uncertainties, again, we can use the acquisition function, which can be our upper confidence bound, in order to choose the next location for measurement. So we acquire data, measure spectrum at few location, define scalarizer, train the model, build acquisition function, and then rinse, wash, repeat. So this is the example how it works. So in this case, our scalarizer is the ratio of this peak to this peak. And what you see here is essentially the experiment where the microscope chooses at which locations to take the next measurement. And you can see that it chooses locations on the edges, which makes sense because this is where our edge plasmon is expected to manifest. What's interesting is that it picks this edge, but not this edge and not this edge. So we don't have time to talk about it, but there are some reasons of why, and then there are some ways to structure the workflow to allow for that. So we can run, of course, the deep kernel learning workflows for any other parameters. So for example, this is the example of the deep kernel learning when we choose the scalarizer, the area under the peak. So in this case, it just explores the whole flake, not only edges. And basically, it gives us some confidence that the whole approach works. So again, a useful exercise is always think in terms of objectives, rewards, value, action, state, and so on. So what's our objectives? We want to understand physics or build optical interface to quantum device and so on. So for fundamental research, impact is very often clear much later. What's our reward? Our reward is minimizing uncertainty in structure property relationship or defining something that, for example, maximizes the intensity of the peak. What is the value? Value is expected reward. It's our scalarizer. What's our action? Position probe at given location. What's the state? Image patch corresponding to this action. What's our policy? It's myopic optimization or upper confidence bound. So you see, any type of automated experiment can be represented in terms of the objective, reward, value, action, state, and policy. Objective can be different. So very often we can do the same things for different reasons, but the rewards, value, action, state, and policies have to be identical. Otherwise, it would be a different experiment. So we are running out of time. And as it happened, I have a PhD thesis in 10 minutes that I have to attend. But let me illustrate a few other things that we can do. So first of all, you can ask, what can we do if our reward policy is not right? Very simple. If we run the experiment, the human can monitor it and constantly shift the reward definition and exploration-exploitation balance. You can ask, what if we go from single-stage myopic decisions to multi-stage decisions? This is a little bit more complicated. So the best book that I can recommend about multi-stage decision is the book by Peter Norvig. So he actually gives the best introduction to machine learning for non-machine learners. Ultimately, what we need to do is to build the world model, action space, the definition of the reward function, and then build the policies. It takes a lot of time and effort. So we would be limited by our capability to represent the physical system via computer science abstractions as opposed by anything else. So my practical advice is, if you want to do that, then we can use things like reinforcement learning or dynamic programming. But practical device is always define the problem in the simplest way. So I build automated experiment workflows in Oak Ridge at UT. I think that currently there are only 3 organizations in US that have this type of experimental capabilities. And there always is a problem of the instrument connections and so on and so forth. But in maybe 6 years working on this type of problems, I have encountered the problems that require reinforcement learning only once. All the other time we can use the myopic optimization. And you may have heard the principle that for machine learning, more data is more important than the algorithm. So for automated experiment, well-defined reward is far more important than the complex algorithm. If you can define your reward well, things will work. If you misspecify the reward, things are not going to work at all. So at this point, I would like to stop, and I will be happy to take questions.